Hello there, and welcome to the Dreamy Science channel. I'm so glad you're here. Maybe it's been a long day, or maybe you're the kind of person who likes to fall asleep thinking about distant planets and drifting moons instead of counting sheep. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your breath slow, your thoughts soften, and your body grow light, as if gravity has loosened its grip and you've begun to float quietly through space. Because tonight, we're going to drift gently through the solar system. Not in a straight line, but in soft spirals, from sunlit planets and dusty rings to shadowed craters and frozen oceans hidden beneath the ice. A story told not in numbers, but in magnetic storms, tilted axes, and moons that hold secrets in the dark. We'll go slowly, gently, just one sleepy fact at a time. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. It helps others find their way here, one sleepy soul at a time. Now, let's begin. Despite being the farthest known planet from the Sun, Neptune hosts the fastest winds in the solar system. These winds tear through its upper atmosphere at speeds that exceed the speed of sound on Earth, roughly 5 times faster than a commercial jet. The winds likely draw their energy from the planet's own internal heat, which continues to radiate outward despite the freezing conditions at its surface. Neptune's atmosphere, composed mostly of hydrogen, helium, and methane, is carved into massive swirling storm systems by those relentless currents. It is a frozen world in constant, supersonic motion. Mars and its Great Canyon. Stretching more than 4,000 kilometers across the Martian equator, Valles Marineris is the largest canyon system in the solar system. It would span the entire width of the continental United States. In places, it plunges more than 7 kilometers deep, over 5 times deeper than the Grand Canyon. Scientists believe it formed through a combination of tectonic stretching, volcanic activity, and erosion. Unlike Earth's canyons, carved by rivers over millennia, this vast scar in Mars's surface opened as the planet's crust cracked and pulled apart. It is a wound from a violent geological past, now frozen in time. Venus without a shield. Despite being similar in size and composition to Earth, Venus lacks one crucial planetary feature: a global magnetic field. Earth's magnetic shield is generated by the motion of molten iron in its outer core, protecting our planet from solar radiation. Venus, however, appears to have a sluggish or possibly solid core, which prevents the dino effect needed to generate such a field. Without this protection, the solar wind constantly bombards Venus's atmosphere, stripping away lighter elements over time. This missing shield helps explain why Venus, once possibly Earth-like, became the furnace world it is today. There's the course of the cloud of the suns of beaches. Diamond rain. Deep within the atmospheres of Uranus and Neptune, conditions may be extreme enough to create something extraordinary: falling diamonds. These icy giants contain thick layers of methane gas. Under immense pressure and heat, scientists believe the methane can break apart, releasing carbon atoms that compress into crystalline structures and rain down toward the core. Laboratory experiments have simulated this process, showing how hydrocarbons can condense into diamond under the right conditions. If the theory is correct, storms of glittering crystals drift through the deep blue darkness of these distant worlds. 104,000 calories of light on the front of the mountain. Earth's moving crust. One of Earth's most distinctive and life-enabling features is its system of plate tectonics, a dynamic network of shifting crustal plates floating atop the mantle. These moving plates create earthquakes, build mountains, and recycle carbon dioxide, regulating climate over geological time. So far, no other planet shows clear evidence of this process. Mars and Venus have surface fractures and volcanic features, but they appear geologically stagnant by comparison. Earth's plate tectonics may be part of what makes it habitable, driving the long-term cycles that stabilize temperature, support oceans, and allow continents to wander across the globe over eons. Asteroids with companions. While we often picture asteroids as solitary wanderers, some actually have moons, smaller bodies orbiting around them. These tiny satellites are usually captured fragments or companions that formed alongside the asteroid. The first discovered asteroid moon was Dactyl, found orbiting the asteroid Ida, revealed by the Galileo spacecraft in 1993. Since then, dozens more have been found, including some with multiple moons, or strange binary arrangements where two asteroids orbit each other. These miniature systems show that even in the vastness of space, gravity can link the smallest of objects into quiet, drifting partnerships. Unlike Earth, Mercury doesn't have a thick atmosphere to retain heat or scatter light. Instead, it has a thin, tenuous shell of particles known as an exosphere, a near vacuum where atoms bounce around without colliding. This exosphere is made of atoms blasted from the surface by solar wind and micrometeoroid impacts, including sodium, potassium, and oxygen. Because Mercury lacks the gravity to hold a real atmosphere, these particles constantly escape into space and are replenished from the surface below. The result is a ghostly, shimmering envelope of scattered atoms, invisible to the eye, but detectable with the right instruments. Every second, the Sun converts over 4 million tons of its own mass into energy through nuclear fusion. In its core, hydrogen atoms are fused into helium, releasing the light and heat that powers our entire solar system. This energy radiates outward in all directions, warming planets, driving winds, and fueling life on Earth. Though the loss is minuscule compared to the Sun's total mass, over billions of years it adds up. For now, the Sun continues to burn steadily, sacrificing a tiny part of itself with every passing second, as it has for over 4 billion years. The beautiful rings encircling Saturn are not permanent. They are gradually falling into the planet, drawn in by gravity and pulled down by Saturn's magnetic field. This process, sometimes called ring rain, involves streams of ice particles and charged material drifting inward over time. Observations suggest the rings may be less than 100 million years old by planetary standards, and could vanish entirely within a few 100 million more. Though they seem timeless and eternal, Saturn's rings are a temporary feature, a shimmering spectacle that will one day quietly fade away. Mars is known for its rusty, desert-like landscape and for the colossal dust storms that sometimes engulf the entire planet. These storms can last for weeks or even months, blocking out sunlight and reshaping the surface. The dust is incredibly fine and can stay suspended in the atmosphere, creating a hazy reddish glow across the sky. Some storms begin as small gusts, but grow rapidly through feedback loops between heat, wind, and topography. In 2018, such a storm ended the Opportunity rover's mission as its solar panels were slowly choked with dust. Even without rain or oceans, Mars remains an active and restless world. Beneath the frozen shell of Jupiter's moon Europa, there is strong evidence for a vast subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that may keep the ocean from freezing solid. The surface is streaked with dark lines and ridges, signs of shifting ice, and spacecraft have detected magnetic signatures and chemical traces that support the ocean hypothesis. What makes Europa especially fascinating is the possibility that this hidden sea could harbor life. It is a dark, alien ocean, warmed from below, sealed beneath ice, yet potentially rich with ingredients for biology. Hello, Olympus Mons. Olympus Mons, the tallest volcano in the solar system, towers nearly 22 kilometers above the Martian plains, almost 3 times the height of Mount Everest. It is so wide it would cover an entire US state. It grew so enormous partly because Mars lacks plate tectonics. On Earth, volcanic hotspots shift over time, creating chains of islands, like Hawaii. On Mars, the crust remains still, allowing magma to erupt in the same spot again and again over millions of years. The result is a single, massive shield volcano that looms silently in the Martian night. Saturn's impossibly thin rings. Saturn's rings stretch more than 280,000 kilometers across, yet in most places, they are less than 100 meters thick, thinner than many city buildings. Made mostly of water ice, the ring particles range from grains of dust to house-sized boulders. When sunlight passes through the ring zone at certain angles, they merely disappear, like a sheet of glass turned sideways. Their flatness is maintained by the planet's gravity, the self-organization of billions of icy fragments, and the influence of small shepherd moons. From a distance they appear solid, but up close they are delicate and ethereal. Heralding giant Earth, the densest planet. Of all the planets in the solar system, Earth is the densest, packing more mass into each cubic centimeter than any other, thanks to its metallic core and silicate mantle. Earth's density is higher even than that of Jupiter, despite the gas giant's far greater size. This high density plays a key role in generating Earth's magnetic field, which arises from the motion of molten iron in its outer core. Our planet's internal structure is compact, heavy, and layered, shaping not just its gravity, but its geology and its protection from space. Though we cannot hear it with our ears, the sun constantly rings with pressure waves rippling through its blazing layers. These oscillations, caused by rising and falling currents of plasma, generate ultra-low frequency sounds far below human hearing. Scientists study these return to the world of scientists under the right and death of creation. By tracking how the waves travel and bounce within the sun's body, researchers can map its internal structure, much like geologists use seismic waves to explore Earth's interior. In a way, the sun is always humming, quietly revealing its secrets through vibration and rhythm. Unlike most planets, Venus spins in the opposite direction, a phenomenon known as retrograde rotation. On Venus, the sun rises in the west and sets in the east. Even stranger, its rotation is incredibly slow. A single day on Venus lasts longer than its year, taking 243 Earth days to complete one rotation, while its orbit takes only 225. Scientists aren't certain why this happened, but one possibility is a massive collision early in its history that altered its spin. Whatever the cause, Venus stands alone, a slow-turning world with a reversed rhythm. All training is a large package of water, or a likely of light of water. How many chairs are there best for delaying? Jupiter and its family of moons. Jupiter is not just the largest planet, it is also the king of moons. Astronomers have identified over 90 natural satellites orbiting it, with new ones still being discovered. Its 4 largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Beyond these giants lies a swarm of smaller, irregular moons, many captured from passing objects. Some orbit backward, some are just a few kilometers across. Together, they form a miniature solar system bound by the planet's immense gravity and history. Mercury is scorching during the day and freezing at night, yet ice is there. At its poles, deep inside craters that never receive sunlight, temperatures remain cold enough for water ice to survive. These permanently shadowed regions act like natural freezers, preserving ice for millions of years. Radar reflections from spacecraft have confirmed the presence of these bright, icy patches. Scientists believe the water may have arrived from comet impacts or ancient volcanic outgassing. In the heart of one of the hottest planets in the solar system, ice quietly persists, locked in darkness, shielded by crater walls from the relentless solar blaze. Pluto's possible ocean. The bright heart-shaped region on Pluto's surface may be more than a scenic landmark. Evidence from the New Horizons spacecraft suggests that a layer of liquid water might lie beneath its icy crust. Though Pluto is far from the Sun and cold enough to freeze nitrogen on its surface, the weight of the basin and signs of geological activity hint at a slushy, convecting interior. If this ocean exists, it may be kept liquid by heat from radioactive decay and insulating layers of ice above. Even in the frozen reaches beyond Neptune, a hidden sea may quietly persist. The asteroid belt is mostly empty. Despite popular imagination, flying through the asteroid belt would not be like dodging rocks in a science fiction film. In reality, the belt is vast and sparsely populated. Located between Mars and Jupiter, it contains millions of rocky bodies, but they are separated by enormous distances. A spacecraft passing through would almost never encounter an obstacle. The entire mass of the asteroid belt is less than 5% that of the Moon. The scattered fragments that make it up are ancient building blocks from the early solar system, remnants that never came together to form a planet. Uranus on its side. Most planets spin like tops, tilted slightly on their axes. Uranus is tipped so far over that it essentially rolls along its orbital path, with an axial tilt of 98 degrees. This means its poles point almost directly at the Sun during parts of its orbit, giving it extreme and bizarre seasons. Each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. The cause is still debated, but it may have been knocked sideways by a massive collision long ago. Uranus's tilted orientation gives it one of the strangest climates anywhere in the solar system. Jupiter's deadly radiation belts. Jupiter is surrounded by the strongest magnetic field of any planet, and within it are radiation belts so intense they would destroy unprotected spacecraft within hours. These belts are filled with charged particles trapped by the planet's magnetic field, forming zones of high-energy radiation similar to Earth's Van Allen belts, but vastly more powerful. Jupiter's largest moons are exposed to this radiation, which affects their surfaces and potential habitability. To survive in orbit around Jupiter, spacecraft must take special measures. It is a beautiful world, but one wrapped in invisible danger. Mixing the Sun owns almost everything. The Sun holds over 99.8% of all the mass in the solar system. Everything else, all the planets, moons, asteroids, comets, and dust, makes up less than 1/4%. Its gravitational pull binds everything in orbit, from tiny grains in the asteroid belt to distant comets drifting in the far reaches of the outer solar system. This immense mass is what fuels the fusion reactions at the Sun's core, converting hydrogen into helium and flooding space with the energy of light. Beyond Neptune lies a scattered population of icy distant objects, many of which are large enough to qualify as dwarf planets. Pluto is the most famous, but it is just one among many. Others like Eris, Makemake, and Haumea share this status, and more candidates are constantly being discovered in the Kuiper Belt and beyond. The number of dwarf planets may vastly exceed that of the 8 classical planets. These small, round worlds are relics of the early solar system, untouched and ancient, orbiting quietly in the cold shadows. Saturn's largest moon, Titan, is the only other place in the solar system known to have stable liquids on its surface, but they are not made of water. Instead, Titan's lakes and rivers consist of liquid methane and ethane flowing across a landscape sculpted by cold chemistry. Its thick atmosphere, rich in nitrogen, forms weather systems that include methane rain and seasonal storms. Some of Titan's lakes stretch for hundreds of kilometers. Beneath the icy surface, scientists also believe a subsurface ocean of water may exist. Titan is a world with familiar shapes, clouds, rivers, coasts, built entirely from alien substances. The moons of Mars. Mars has two tiny, misshapen moons, Phobos and Deimos. They look more like asteroids than traditional moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were captured by Mars's gravity long ago. Their strange orbits and low densities support this idea. Phobos is slowly spiraling toward Mars and will eventually break apart or crash into the planet. Deimos is drifting away. These little moons are quiet passengers in orbit, remnants of a chaotic past. Jupiter's inner glow. Unlike most planets, Jupiter gives off more energy than it receives from the Sun. This internal glow comes from leftover heat from its formation, gravitational energy released when the planet's immense mass collapsed together. Over time, it continues to contract slightly, generating warmth in the process. This heat drives Jupiter's turbulent weather systems, including its giant storms and swirling cloud bands. In infrared light, Jupiter shines brightly, like a smoldering coal beneath its cloud layers. It is not a star, but it came close. A little more mass, and it might have ignited into one. Neptune, found by mathematics. Unlike other planets, Neptune was not discovered by simply looking through a telescope. Astronomers noticed irregularities in Uranus's orbit, tiny deviations that couldn't be explained by known gravity. Two mathematicians working independently in the 1840s used these strange motions to predict where a hidden planet must be. When astronomers pointed their telescopes toward that calculated position, Neptune was there. Compact of light is dead. It was a triumph of celestial mechanics, confirming that unseen forces could be mapped through mathematics alone. Neptune was the first planet found on paper before it was seen through glass. Saturn's polar hexagon. At Saturn's north pole, a massive cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across, wider than the entire Earth, and has persisted for decades, possibly centuries. Scientists believe it forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. In laboratory experiments, similar shapes appear when rotating fluids move at different speeds. The fact that such a precise geometric shape can emerge naturally in a planetary atmosphere remains one of the more surreal and elegant phenomena in the solar system. The Sun's visible surface burns at around 5,500 degrees Celsius, yet its outer atmosphere, the corona, can reach over 1,000,000 degrees. This unexpected rise in temperature has puzzled scientists for decades. One theory suggests that magnetic waves from deep within the Sun transfer energy upward and heat the corona from below. Another possibility involves tiny solar explosions called nanoflares, each releasing a small burst of energy that collectively heats the outer layers to extraordinary temperatures. Either way, the Sun's outer atmosphere glows with a mysterious, searing heat that far exceeds its visible surface. The Kuiper Belt's frozen archive. Beyond Neptune lies a wide ring of icy objects known as the Kuiper Belt. It stretches billions of kilometers from the Sun and is home to countless frozen bodies, including Pluto, Eris, Haumea, and Makemake. These are not stars or planets, but ancient remnants from the solar system's formation, some spherical and classified as dwarf planets, others irregular, tumbling slowly through space. The Kuiper Belt is far colder than the asteroid belt and contains more primordial ice. It is a fossil zone, a frozen archive of the materials that built the outer worlds. Far beyond the Kuiper Belt, even beyond Pluto's farthest reach, lies a hypothetical shell of icy bodies known as the Oort cloud. Though never directly observed, this vast sphere of frozen debris is thought to encircle the solar system and extend nearly a light year away. It is the likely source of long-period comets, which appear from the depths of space on unpredictable orbits. These distant objects are only weakly bound to the Sun, and a passing star or galactic tide could send one hurtling inward. If the Oort cloud exists, it marks the true outer edge of the Sun's gravitational influence, a distant halo of icy wanderers. Jupiter's moon Io is a seething, restless world covered in active volcanoes. Its surface is constantly reshaped by eruptions of molten sulfur and rock, painting the landscape in vivid yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is driven by tidal heating. Io is squeezed and stretched by Jupiter's immense gravity, along with gravitational tugs from neighboring moons. The friction from this constant flexing heats the interior, powering its furious geology. Unlike Earth's slowly cooling crust, Io's surface is young, volatile, and always changing, a lava-lit moon with a molten heart. Handrel pow, 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 pow. I'm Sydney Burney, and Tom F. Brown. Triton, moving in reverse. Triton, Neptune's largest moon, orbits its planet in the opposite direction of Neptune's rotation, a motion called retrograde orbit. This backward path suggests Triton did not form alongside Neptune, but was likely captured from the Kuiper Belt. That capture may have caused dramatic upheaval, potentially disrupting Neptune's original satellite system. Triton is also geologically active, with cryovolcanoes that spew icy material into space and a thin atmosphere that expands and contracts with the seasons. Cold, distant, and moving in reverse, Triton is a world that defies expectations at every turn. No other rocky planet in the solar system has such a relatively large satellite. The Moon is about 1/4 the diameter of Earth, a ratio more typical of dwarf planet systems. Most scientists believe it formed after a Mars-sized body collided with the young Earth, ejecting debris into orbit that eventually coalesced into the Moon we know today. This close partnership has profoundly influenced Earth's tides, climate, and rotational stability over billions of years. Our Moon is not just a companion, it is a cosmic legacy of ancient collision. Although we often imagine the planets moving in perfect circular paths, their orbits are actually ellipses, slightly stretched, with the Sun offset from the center. This means each planet has a point where it is closest to the Sun, called perihelion, and a point where it is farthest, called aphelion. For most planets, the difference is subtle, but for others, like Mercury and Pluto, it is more dramatic. These variations influence seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the 1600s, reshaping our understanding of the solar system's elegant mechanics. However, our engagement is something that only once again. Long-period comets, the kind that appear only once every few thousand years, are believed to come from the Oort cloud, that distant shell of icy debris nearly a light year from the Sun. These comets travel on elongated, loosely bound orbits and are often dislodged from their resting places by passing stars or the subtle pull of galactic tides. When they fall inward toward the Sun, they can light up with spectacular glowing tails, visible even from Earth. Some may have spent billions of years drifting in darkness before being nudged into motion. Their bright returns are fleeting glimpses of the solar system's most ancient and untouched matter. In about 5 billion years, It will exhaust the hydrogen fuel in its core and expand into a red giant, engulfing the inner planets. After shedding its outer layers in a glowing shell of gas called a planetary nebula, the core that remains will become a white dwarf, a dense, Earth-sized remnant made mostly of carbon and oxygen. This white dwarf will no longer produce energy, but will slowly cool over trillions of years. It will be the final form of our sun, a glowing ember in the darkness, marking the end of its long stellar journey. Stasis. Mars has seasons. Though colder and with a much thinner atmosphere, Mars experiences seasons much like our own planet. This is because Mars has a similar axial tilt, about 25 degrees compared to Earth's 23. As it orbits the Sun, this tilt causes sunlight to strike different hemispheres more directly at different times of year. The result is a cycle of spring, summer, autumn, and winter, with varying temperatures and light levels. Martian seasons also influence polar ice caps, dust storm patterns, and subtle changes in air pressure. They unfold more slowly than on Earth, however, because Mars takes nearly twice as long to complete a year. Jupiter's moon Ganymede is the largest natural satellite in the solar system, even bigger than the planet Mercury. With a diameter of over 5,000 kilometers, Ganymede has a rocky core, a possible subsurface ocean, and a crust covered in ridged ice and ancient scars. In Euclid, it is the only moon known to have its own magnetic field, which creates shimmering auroras in its thin atmosphere. Scientists believe Ganymede may have multiple layers of ocean sandwiched between sheets of ice, forming a complex and layered interior world. Despite its size and richness, it remains quiet and dark, orbiting deep within Jupiter's magnetic grasp. Very clearly, Pluto and Neptune's orbital dance. Although Pluto is usually the most distant classical dwarf planet, its orbit is highly elliptical, meaning it sometimes travels closer to the Sun than Neptune. This last occurred between 1979 and 1999, when Pluto was temporarily the eighth planet from the Sun. Even so, the two worlds never collide or come dangerously close, because their orbits are in resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This gravitational choreography keeps them in a stable dance, their paths never truly crossing, a delicate balance governed by celestial rhythm. Listen, the Sun's breathing cycle. Roughly every 11 Earth years, the Sun's magnetic field flips, the north and south magnetic poles switch places. This process, known as the solar cycle, is tied to the Sun's internal dynamics and affects solar activity, including sunspots, flares, and energetic outbursts. At the peak of the cycle, called solar maximum, the Sun is more active, with more intense radiation and magnetic storms. As the cycle winds down, activity decreases, eventually reaching solar minimum. These cycles influence Earth's upper atmosphere, satellite operations, and even the brightness and frequency of auroras. The Sun's magnetism pulses and flows, like a slow magnetic heartbeat. Leaving the solar system, escaping the pull of the Sun, is no small task. Spacecraft like Voyager 1 and 2, launched in the 1970s, have only recently entered interstellar space, the region beyond the heliosphere. These missions took more than 40 years to reach that boundary, traveling outward at speeds exceeding 60,000 kilometers per hour. The Voyager probes have crossed the orbits of the planets, passed through the Kuiper Belt, and continued into the dark. They carry instruments still functioning, as well as a golden record filled with the sounds of Earth. They are our quiet ambassadors to the galaxy. Earth's invisible shield. Surrounding our planet is an invisible magnetic field, generated by the movement of molten iron in Earth's outer core. This field deflects charged particles from the Sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would gradually erode our atmosphere, as it likely did on Mars. The field also funnels some particles toward the poles, where they interact with atmospheric gases and produce auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere is a dynamic, essential shield for both life and climate. This slow retreat is caused by tidal interactions. The gravitational pull between Earth and the Moon creates bulges in our oceans, which in turn nudge the Moon slightly outward. In the distant past, the Moon was much closer and appeared significantly larger in the sky. As it recedes, our days gradually lengthen and eclipses become less frequent. Billions of years from now, total solar eclipses will no longer be possible. The sky is changing, even if we cannot yet feel it. Enceladus and its gazers. Saturn's small moon Enceladus hides a spectacular secret. From its south pole, towering gazes of water vapor and ice crystals erupt into space through cracks known as tiger stripes. These plumes are powered by tidal heating beneath the surface. Friction caused by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and signs of hydrothermal activity, raising the tantalizing possibility of life. Some of the water escapes into space and helps replenish Saturn's faint E-ring, creating a living connection between moon and planet. Many are loose collections of stones, gravel, and dust, held together only by gravity, structures known as rubble piles. These fragile bodies can form after collisions shatter larger asteroids, with the debris slowly coming back together over time. Rubble pile asteroids can have large internal voids, spin strangely, and change shape under pressure. Missions like Hayabusa 2 and OSIRIS-RX have visited such bodies, confirming their delicate, porous nature. These asteroids are not monolithic relics. They are chaotic assemblages, ancient drifting ruins of early planetary construction that barely hold themselves together. Mercury is a small planet, but it has an unusually massive iron core, making up about 80% of the planet's radius, a far larger proportion than seen in Earth or Venus. The reason remains uncertain. Some scientists think Mercury once had a thick rocky mantle that was stripped away by a giant impact. Others believe it formed close to the Sun, where solar forces favored the accumulation of heavier elements. The result is a planet with a thin crust, a huge core, and a weak magnetic field, a metal-heavy survivor from the solar system's chaotic youth. Among the rocky planets, only Mercury and Venus are without natural satellites. Venus's situation is particularly puzzling. It is roughly the same size as Earth, which has a large moon, yet Venus has none. Some theories suggest it may have once had a moon that fell back into the planet or was lost in a collision. Others argue that Venus's slow retrograde rotation might prevent stable orbits from forming. Whatever the cause, Venus orbits alone, a bright, cloud-wrapped world with no lunar companion in its twilight sky. While Earth has just one moon and Mars has two tiny ones, the giant planets of the outer solar system are surrounded by sprawling satellite families. Jupiter and Saturn each have dozens of confirmed moons, ranging from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host many icy moons, some with complex orbits and hidden oceans beneath their frozen surfaces. The farther from the Sun you go, the more moons you'll find, a reminder that gravity gathers companions in the cold. 114. Jupiter's ancient storm. The Great Red Spot is a massive storm swirling in Jupiter's southern hemisphere, wide enough to contain 2 or 3 Earths. It has been raging for at least 350 years, possibly much longer. first observed through early telescopes in the 70s. The storm has gradually changed in size over time, but remains powerful. Its reddish hue may be caused by complex chemical reactions in Jupiter's atmosphere, triggered by sunlight and high-altitude compounds. Wind speeds exceed 400 kilometers per hour along its outer edges. While Earth's storms last days or weeks, this Jovian tempest spans centuries, trapped in the planet's turbulent belts. Although Neptune lies far from the Sun, it is not a frozen, inert world. It radiates about 2.6 times more energy than it receives. This internal heat drives strong winds and storm systems, including the fastest recorded winds in the solar system. The exact source of Neptune's warmth remains uncertain. Possibilities include residual energy from its formation, slow gravitational contraction, or radioactive decay within its core. Despite its extreme distance, Neptune is a world of surprising energy, a planet with a cold exterior and a warm, restless interior. Our planet is unique in that water exists naturally on its surface as a solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and vapor, all coexisting and cycling through the atmosphere, land, and sea. This balance is crucial for life and is regulated by Earth's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms, icy crusts, vapor in thin atmospheres, or hidden subsurface oceans, but none show the same dynamic, planet-wide presence. On Earth, water flows, freezes, and evaporates in a never-ending, life-sustaining dance. As the solar wind flows outward from the Sun, it eventually collides with the interstellar medium, the thin gas and dust between stars. This boundary is called the heliopause, and it defines the outer edge of the Sun's protective bubble, the heliosphere. Beyond this point, the pressure from other stars and galactic particles becomes stronger than the solar wind. Voyager 1 crossed this boundary in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the Sun's gravity still extends much farther, the heliopause marks the end of its energetic reach, the final breath of solar influence before deep space begins. Our entire solar system is moving through a region of space called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It is part of a larger structure known as the local bubble, formed by ancient supernova explosions. As the Sun travels through this cloud, the heliosphere acts like a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions can affect cosmic rays and Earth's climate over long timescales. We are not sitting still in space. We are sailing slowly and silently through a galactic fog. Olympus Mons activity. Active moons activity is not limited to planets. Several moons in the solar system show signs of internal energy and surface change. Io, a moon of Jupiter, is riddled with active volcanoes fueled by tidal heating. Enceladus, orbiting Saturn, vents plumes of water vapor into space. Europa and Ganymede likely have subsurface oceans stirred by internal warmth. Even distant Triton shows signs of cryovolcanism, icy eruptions driven by shifting pressures below. These moons are not static ice balls. They are restless worlds with geology, chemistry, and perhaps even the potential for biology hidden beneath their frozen surfaces. Though small and cold, Pluto has a thin atmosphere, composed mostly of nitrogen, with traces of methane and carbon monoxide. When Pluto approaches the Sun in its elliptical orbit, surface ices sublimate into gas, forming a hazy envelope that expands into space. As it moves farther out, the atmosphere cools and collapses, freezing back onto the surface like frost. This cycle repeats over Pluto's 248-year orbit. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a layered blue haze, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. The Sun's fiery heart, deep inside the Sun, at its center, temperatures soar to over 15 million degrees Celsius. Here, hydrogen atoms are compressed under immense pressure until they fuse into helium, releasing enormous amounts of energy. The energy generated in the core takes hundreds of thousands of years to reach the surface, bouncing through layers of dense plasma. Once it escapes, it travels across space in just over 8 minutes to reach us. The Sun's radiant calm hides an unimaginably hot and violent heart. Its closest approach to the Sun slowly shifted over time, more than Newtonian physics could account for. In 1915, Albert Einstein's theory of general relativity provided the solution. According to relativity, massive objects like the Sun warp the fabric of space-time, subtly altering the paths of nearby objects. The measured effect on Mercury's orbit matched Einstein's predictions exactly. This became one of the first experimental confirmations of his revolutionary theory, a triumph of mathematics explaining a quiet quirk in the motion of a scorched, rocky world. The daily rise and fall of ocean tides on Earth are largely caused by the gravitational pull of the Moon. As its gravity tugs on Earth's oceans, it creates bulges on the side facing the Moon and on the opposite side. As Earth rotates, these bulges move across the globe, producing high and low tides. The Sun also plays a role, creating stronger spring tides and gentler neap tides depending on its alignment with the Moon. Tidal forces not only affect oceans, they can subtly shift the Earth's crust and influence the planet's own rotation. The Moon's silent pull keeps our oceans in motion. Astronomers have noticed that some distant objects in the Kuiper Belt follow clustered, elongated orbits that cannot be easily explained by the known planets. One leading theory is that a large, as yet undetected planet, sometimes called Planet 9, may be influencing these distant paths with its gravity. If it exists, this hidden world would be several times the mass of Earth and orbit far beyond Pluto, taking thousands of years to complete a single revolution. No direct evidence has yet confirmed it, but telescopes are searching. If found, it would reshape our understanding of the solar system's outer architecture. Jupiter's moon, Callisto, appears quiet and cratered, an ancient surface seemingly untouched by recent geological activity. But deep beneath that frozen crust, scientists suspect a subsurface ocean may exist, kept liquid by internal heating and residual warmth from formation. Magnetic readings from the Galileo spacecraft hinted at a conductive layer beneath the surface, consistent with salty water. If confirmed, Callisto would join Europa, and Ganymede as another hidden ocean world. Though less celebrated, Callisto's deep, dark sea could quietly contain the ingredients for life, sealed beneath a shell of ice and time. Although Mercury is the closest planet to the Sun, Venus holds the record for the hottest surface temperatures. This is due to its incredibly thick atmosphere, composed mostly of carbon dioxide, which traps heat in a runaway greenhouse effect. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead. The dense clouds reflect sunlight, but also prevent heat from escaping. Meanwhile, Mercury, with its thin exosphere, has no such insulation and cools rapidly on its dark side. Venus's searing heat is not just about proximity to the Sun, it is about the power of a trapped atmosphere. Hanasols, open beams, and stars' antisymmetry. Saturn, lighter than water. If you could place Saturn in a giant cosmic bathtub, it would float, not because it is hollow, but because its average density is less than that of water. Saturn is composed mostly of hydrogen and helium, giving it a lightness despite its massive size. Its volume is enormous, more than 700 times that of Earth, but its mass is only about 95 times greater. This low density gives Saturn a soft, diffuse structure, with rapid rotation that flattens it at the poles and causes it to bulge slightly at the equator. It is a giant of gas, gently puffed into shape by gravity and motion. Hurry will fast and get some contained gravity. War and mountain solar structure. Solar flares and earthly effects. Solar flares are sudden, powerful eruptions of energy from the sun's surface, often linked to sunspot activity. These outbursts release intense bursts of radiation across the electromagnetic spectrum. When directed toward Earth, they can disturb the upper atmosphere, affecting GPS systems, radio communications, and satellite operations. In extreme cases, they can trigger geomagnetic storms capable of damaging power grids. While Earth's magnetic field offers significant protection, solar flares remind us that the sun is not a steady light source. It is a dynamic, volatile star that occasionally sends ripples of energy pulsing across the entire solar system. Andrew Auroras and the solar cycle. Auroras, the shimmering curtains of green, red, and violet light near Earth's poles, are caused by charged solar particles interacting with Earth's magnetic field and atmosphere. These displays become more frequent and intense during periods of high solar activity, which follow an 11-year cycle. During solar maximum, increased sunspot activity and solar flares send more particles toward Earth, feeling brighter auroras. During solar minimum, the lights grow quieter. The sun's magnetic fluctuations ripple outward, and we see them painted across the sky, a reminder that space weather can be beautiful. Comet tails point away from the sun. As a comet approaches the sun, its icy surface begins to release gas and dust, forming a glowing tail. But this tail does not trail behind the comet like smoke. It points away from the sun, no matter which direction the comet is moving. This is because solar wind and radiation pressure push the material outward, forming two distinct tails, a curved dust tail and a straight, bluish ion tail. The result is a luminous, windswept signature, tracing the invisible force of sunlight through the darkness of space. Launched in 1977, Voyager 1 now travels through interstellar space, farther from Earth than any other human-made object. Attached to its side is a golden record, a phonograph disc containing sounds and images chosen to represent life on Earth. It includes greetings in dozens of languages, music from around the world, and recordings of waves, birdsong, and laughter. Designed by a team led by Carl Sagan, the record is meant for any intelligent beings who might someday find it. It is a message in a bottle, cast into the galaxy, a quiet greeting from our pale blue dot. While the planets orbit the sun itself is also moving, revolving around the center of the Milky Way galaxy. It takes roughly 225 to 250 million years to complete one full orbit, a journey sometimes called a cosmic year. During that time, the solar system drifts through different regions of interstellar space, potentially passing through galactic arms, star-forming regions, and clouds of gas and dust. This motion may influence comet activity and, on longer time scales, even Earth's climate. We are not fixed in space. We are part of a vast, slow spiral, riding the galaxy's arm like a cosmic carousel. Coming to rest. And so our quiet journey through the solar system comes gently to a close. From the inner world scorched by sunlight to the icy moons that whisper in the dark, we've wandered together through orbits, storms, and shadows, one sleepy fact at a time. We watched ice survive inside the hottest planet. We floated past a canyon that spans a continent and a storm that has raged for centuries. We found hidden oceans in the most unlikely places and followed ancient comets making their slow return from the edge of everything. In all of it, there was that steady, quiet feeling of perspective, The solar system is not just a collection of rocks and gas and ice. It is a living, breathing, ever-changing family of worlds, each one shaped by time, gravity, and the long reach of the sun. If these facts have helped you unwind and find some peace, a gentle like or a quiet comment before you sleep is always welcome. It helps others find their way here too. But now, you don't need to hold on to any of it. Let the images soften. Let the planets drift. Let your jaw unclench, your shoulders drop, and your breathing find its own easy rhythm. The universe is patient. It will still be there in the morning. Sleep well, and good night.